G'day. I'd like to have a bit of a chat with you about surface area. So surface area is the total, well, it's a measurement of the total surface of an object. It is particularly useful if you want to paint some sort of three-dimensional object or tile it, or what else are we going to do? I don't know, gold plate it. You need to know the surface, the amount of area that you are going to be applying this stuff to. Surface area is one of those things that does actually turn up a fair bit in life. So I'm going to start off with a couple of simple objects that suit formulas, ones that you may or may not have seen before. This here, I hope you recognise that that's a cube. Is all its sides of the same length? Now, tell me, what would the area of the front of this thing be? This front face here, it's a square. Hopefully by now you'll be able to tell me that the area of a square is either the length squared or the side squared. I'll just call it S squared to represent the side. How many sides are there on a cube? 6. So what's the area of each of those sides? Well, it's going to be 6 squared, isn't it? So I can write a formula for the surface area of a cube. It looks something like this. Surface area equals 6 S squared. I could take this further. Let's say you had the side length there. Let's say I told you that's 3 millimeters. This is a very small cube. Some sort of jewellery, I don't know. I don't understand those things. So what we do now, this is how I like you to do maths, how you're going to get in the habit of for the future, is we've written the formula. Now we're going to put the values in, then we're going to get the answer. So that'll be 6 times. Remember, where you don't see a symbol, it means multiply. So it'll be 6 times 3 squared. Indices first, 3 squared is 9. Remember, squared means multiplied by itself. Then 6 times 9 gives us 54. So you get 54 millimeters squared. If you were to gold plate that cube, you need to cover 54 millimeters squared. Right, second example we'll do a rectangular prism. This is another one that suits a formula that you can use for the whole thing. 3 dimensions in this object. Hopefully by now you're okay with the idea that we use length, width and height. And I might put some values on this. I'll make it a shoebox. I'm going to make it about 30 centimeters here. I'm going to make it about 20 centimeters here and about 15 centimeters here. And I can hear you screaming from here. You're going, "Sir, that's not to scale." That's right, it's not to scale. That's why you've got to be careful. We're testing your mathematics here, not how beautiful a drawing I can do. Right, so anyway, let's think of there's 3 different faces here. Look, if I draw some markers in here, should be able to tell that there are 6 faces in total, right? There's the front and the back, there's the left and the right, there's the bottom and the top. There's 6 faces here. And of them, a number of them are different. Let's think about this face at the front here. What would the area of this face on the front be? Its length in this direction and its height in this direction. So the area of this front face will be length times the height, whatever that is. What about on the top? This one up here. It's the length in this direction and it's the width in this direction. So again, the area, like any other rectangle, remember rectangles, just the 2 dimensions multiplied together, you're going to get length times width. And that leaves us with this third one here. In this case, you've got width in this dimension and height in this one. So HW. All right, so next thing you've got to notice is, well, that face on the front, the area that's on the front is going to be the same at the one at the back. So length times height is going to be the area at the front and it's going to be the area at the back. You've got 2 lots of that. And what about the top? The area there has to be the same as the bottom. And this one I've shown on the right hand side, the area there has to be the same as the left hand side. So all in all, you can write the surface area for this thing as being 2 lots of each of them. 2 lots of length times width 2 lots of length times height and 2 lots of h times width. That'll give you the total surface area of that object. There's another way of writing it. I haven't taught you the algebra on how to convert between these two yet. Well, I've hinted at it with some of you. But I could also write that as 2 times, in brackets, length height, and height width. Because, think of it, if you added those 3 faces together and then just multiplied the whole lot by 2, you're still going to get the same thing, aren't you? That face plus that face plus that face, add it together, multiply it by 2. You're going to get the surface area of the whole object. That's all that formula says. I'm going to use that one though, because that's the one you're more likely to be familiar with at this stage. And I'm going to show putting in the values and calculating the surface area. So remember, where we don't see a symbol, it means multiply. So 2 times L, the length is 30, times width, the width is 20, plus 2 times the length is 30, the height is 15, plus 2 times the height is 15, and the width is 20. Now this is going to be lots of fun here, because I haven't done this in preparation. Let's hope I get my numbers right. So 2 times 30 times 20 should be 1200. So 30 times 20 is 600, doubled. That's how I did it then. What about this one? 2 times 30 times 15, well, that's going to be 450. Doubled is 900. And here, 2 times 15 times 20, well, that's 300. Double 300, you get 600. So that's 1500 in total, 2700 centimeters squared. That better be right, because I don't want to re-record this video. So there you go. The total surface area, adding up the area of every face of this object, is 2700 centimeters squared. Okay, now for a whole range of other three-dimensional objects, there aren't always formulas to work out the surface area. I mean, sometimes we can make up strange formulas for that purpose, but a lot of the time you need to be able to take a three-dimensional object and split it down into its individual components and work out the area of the individual components. So what I'm going to do right now is just here for example, some sort of triangular prism. I mean, there's 2 triangles there at the front and back. You need to remember how to calculate an area of a triangle to do that. The rest are rectangles. You need to know how to work out the area of a rectangle. This here was meant to be some sort of parallelogram that's 3-dimensional going backwards. Again, might need to know how to work out the area of a parallelogram there. That there is half a cylinder. Now, given that even the area of a circle is not in the Year 7 curriculum, it's actually in Year 8, I'm being a little bit naughty there, but that's okay. So what I'm going to do here quickly is I'm going to run through the objects that you should know how to find an area of. I've gone through them all in class, so I'm not going to do it quickly. Just a reminder, this is how you do it, this is how you show the working. So first off, I'm going to start with the square. All sides the same length. Area is simply the side squared. Sometimes you see that as L squared instead of L for length instead of S for side. Doesn't matter, same deal. Right, so let's say I made that 6 meters. Second step, put in the value. Third step, 6 squared is 36. Area is 36 meters squared. Again, same pattern every time. Formula, substitute the value in the formula, give me an answer. All right, so that's the area of a square. Next up, predictably, I'm going to do a rectangle. See, some of these make sense in a strange way too. Look, let's say I made this 3 centimeters by 1, 2, 3, 4, 5 centimeters. I mean, picture that for a moment. If I split, oh, that was a mess. If I split this up into 5, say it was 5 centimeters long, and this into 3, say it's 3 centimeters long, how many little rectangles do you get? 15, right? 15 little centimeters squared pieces. So with that in mind, area of a rectangle, as you've always known, is length times width. So I write the formula. I put in the length is 5 times the width that's 3. And funnily enough, 5 times 3 does give you 15 centimetres squared. And what that means, of course, is the area, the surface, is going to be 15 lots of little 1 centimetre by 1 centimetre blocks, right? Centimetres squared, it's a surface. All right, so that's square and rectangle. Other one that you need to know, triangle. All right, triangle, as I've shown in class, you have to be careful. The formula is, of course, area is half base height. But importantly with the height, that height needs to be the perpendicular. The perpendicular height means it's at right angles to the base. So there's your height, there's your base, needs to be at right angles. So you've got to be careful which measurement you take. We had a lot of fun with that in class, doing examples there where I tried to trick you up, trying to make sure you realise which measurement you should be using. So in this case here, as I'm just doing a quick one, it's going to be a huge triangle. I'm going to make it 4.2 kilometres in this direction, and I'll make it 4 kilometres in here. So putting in the formula, it's a half times the base, which is 4.2, times the height, which is 4, perpendicular height, and half of 4 is 2. Double that, it'll be 8.4 kilometres squared. Right, so there's some of the basic objects you should know the area of: cube, rectangle, and triangle. And just a moment, I'll be back. Okay, here we go. The additional object here is a parallelogram. You need to be able to work out the area of a parallelogram. Parallelogram is a variant of a rectangle. Essentially, if I draw a line here and a line here, in a parallelogram, that should be exactly the same as that. So the area of a rectangle is length times width. The area of a parallelogram is very similar, but it needs to be the perpendicular height. It needs to be the height here, not the height here. If you use the length there, what would happen? Would your area be higher or lower than it should be when you work it out? The answer is higher. It would give you a higher number than your actual area if you used the length there. So again, you need the perpendicular height, like we had the situation with the triangle. So we tend to write the parallelogram area as BH, where again, H is the perpendicular height. It needs to be at 90 degrees there to the base. Same process. Once we've done that, we state the formula, we put in the values, base is 12, height is 7. We calculate that out, we get 84 millimetres squared. So there'd be 84 little 1 millimetre by 1 millimetre bits in that object. The second object here is extension for year 7, but I am including it anyway. It is called a circle. Now, the formula for the area of a circle is pi r squared, pi being this amazing irrational number. 3.141592653589793, and I'm afraid that's all I know. Your parents can probably beat me at that. So here we go. Now, the trick I've done with this question too is I didn't give you r. R means the radius. That's not the radius. What is it? It's a diameter. All right, so here, the diameter is 13. So what does that mean the radius is going to be? The radius has to be half of that. So the radius will be 6.5 meters. That's the value that we're going to put in the formula. So area will be pi times 6.5 squared. At this point, you need a calculator. Really want you to use the proper value of pi, which is under the times 10x button on the Casios normally. So we go shift the 10x button and it puts a proper pi there. That's what you want. So it's going to be pi times 6.5 squared. And there we go. I'm going to use the approximately equal signs because it's rounding. Whenever you involve pi and you do that in a calculation, because pi goes on forever, you do end up doing a little bit of rounding. So this is approximately 132.73, and what are our units? Meters squared. It's a big crop circle. Right, so the other thing, you can use other objects than that. You can find the area of a lot more objects than that. Things like hexagons, octagons, all that sort of stuff. But it's not covered at this stage in the curriculum. In year 8, 9, you cover rhombuses, kites, and sectors, which is just part of a circle. And none of that's particularly hard, by the way. It's harder when I sit there and make you have to find an unknown side using Pythagoras, which is actually in year 8 as well. That's harder stuff. But if you do have unusual shapes that you want to use, my recommendation is look them up on Google and see if you can find a reliable site that gives you some good suggestions there. Check them with me if they give you weird answers. It's all right. Have some fun. Now, the last bit here is about composite shapes. We haven't covered that in class at this stage. Composite shapes is just a situation where you combine more than one shape. And I'm going to do 2 quick examples of it. So the first one here, what 2 shapes that you know are involved in that? Well, if I draw a line here, it might be a bit more apparent. What do you got? You got a rectangle and triangle. So here, if it's 8 meters along here, but 10 meters along the top, that tells us that the distance in here has to be 2. That's probably going to be useful to us. Better draw a right angle there if I'm going to be really technical about it. The examples in the book don't say that, but if they don't show a right angle, then you're assuming it. These formulas assume. The formula of a rectangle, it assumes you've got right angles in there. All right, so if I was to write a fancy formula for this, I'd say the area is length width, so the rectangle, plus the area of a triangle. So it's a rectangle plus a triangle. And then you can put all the values in and see what we get. All right, so when I'm looking at the rectangle here, it's 8 by 4. When I'm looking at the triangle here, it's a base of only 2 and a height here of 4. So 8 times 4 is 32. A half of 2 is just 1. Times 4 is 4. So we're going to get 36 meters squared. Okay, so that's the first example. And yeah, I mean, I didn't mention that at the start, but let's think about it logically. If you wanted the area of that whole object, it's going to be, well, whatever amount of the surface is there plus the surface there. You just add the areas together and you'll get the total area. Just like we do the total surface area on those 3-dimensional objects. You add the area of this surface to the area of this surface, to the area of this surface, and so on. You can just add the areas together to get the total area. Let's look at this one down here. Now this time we've got these strange markings on, means they're all the same size. And what are our 2 primitive objects we're dealing with this time? It's a square and a triangle. So if I was to write a fancy formula for this one, I'd say, well, the area is going to be side squared. You can make that L squared, I don't care. Of the square, but this time subtract that triangle. So it's going to be the total surface that square would be, take away that triangle. All right, so from there, let's get the square. It's 5 by 5, so 5 squared. Take away the triangle, which is 1/2 times the base there, the length across the top should be 5. And the height should be 2. So it's going to be 5 squared, which isn't 10. It's 25, remember? Squared means multiplied by itself. It'll be 25. Take away, 1/2 of 2 is 1. 1 times 5, it'll just be 5, which gives us 20 meters squared. Right? That's your answer. All right. So that's how you deal with composite shapes with 2 examples. Now, they're the sort of skills that you'll need if you've done some very strange objects in terms of your nets for your project. and the sort of calculations you might have to do. If you've dealt with shapes that aren't on here, by all means Google. I'm happy to give you a couple of tips here and there, and particularly don't want you doing anything impossible. Please don't try anything impossible at this stage. Leave that for at least, year 9 or something. You agree? Yeah. All right. Thank you. Bye.